Another example, sketch. Let's sketch the graph. And let's see, let's do the function f of x. I'm gonna keep stressing ln just because ln is gonna be popping up several times in your calculus courses. So I want you to be familiar with that. Okay, so ln of x minus 2 plus 1. Okay, so if we want to graph this function, you should understand that this is coming from the natural log function, and we're doing some transformations to it. Okay, how many transformations are we doing to this graph? It's a total of 3 transformations, right? So what are we doing? We're doing a reflection with respect to the x-axis. That's what the negative in front means. Then we're going to the right 2 units. That's what the x minus 2 represents. And then finally, we're shifting this function up 1 unit. That's what the plus 1 means. Okay. All right. And I said in that order because you should create the habit of doing your reflections and stretches before you start moving around. So before I go to the right 2 units, you could go to the right and then reflect. But I prefer to reflect first and then I move. Okay? It's easier to reflect in the original position than move and then reflect. Make mistakes that way. All right. Anyways, let's graph this, and we're gonna do it, using transformations. So we're gonna start with the basic function, which is the natural log of x, and then let's write the sequence of steps. And from here, we're gonna go to our second step, which would be a reflection. Then from here, we're gonna go to our third step, which is a shift to the right 2 units. That's what happens when you replace x by x minus 2 in your function. And then finally, the last transformation is we take the picture that we get a number 3, and we're gonna shift it up 1 unit. That's what the plus 1 is telling us. Take whatever picture you have in number 3 and move it up. All right, so once we have this plan, then it's just writing the corresponding pictures. Okay. So we begin with the basic graph. You just have to have knowledge of the basic graph, which is like this, right? ln of x. And we need a couple of points in the graph to follow along. So I'm gonna write 2 points. So this is the point 1, 0. And remember the other special point is when you plug in e, you get 1. Okay, e, 1. So we're gonna be following along those points. All right, so from 1 to 2, what's happening? We're multiplying by -1. So that's a reflection. So reflect about x-axis. So you just have to go ahead and flip the picture with respect to the x-axis. So let's see, x and y. So the point 1, 0 stays there, but then whatever is above now comes below, whatever is below now goes above. So e, 1 becomes e, -1. Maybe more this way. So this one stays here, and then e, 1 becomes e, -1. And then when you do the reflection, we're gonna get this picture. Okay. Which, by the way, it looks awfully like a natural log with base, like a logarithm with base less than 1, right? And actually, that's true. This right here, what you see here, so minus ln of x is actually the same thing as log base 1 over e of x. Okay, that's why we see that picture. We're gonna see that when we study the properties. Okay. Anyways, now we're just following the transformations. And from 2 to 3, what's happening? We are replacing x by x minus 2. That's what's different. So that means that we're gonna go right 2 units. All right, so how do we do this? Remember, we first move our points and then we graph the picture. Now remember, we're doing a horizontal shift, and this function has a vertical asymptote. Whenever you move a function horizontally, if it has vertical asymptote, the asymptotes move with the function. So the first, number 2 has a vertical asymptote at x equals 0. We're moving everything to the right 2 units, so now we're gonna have an asymptote at x equals 2. Now vertical asymptote is moved. Instead of being the y-axis, is now the line x equal 2, and everything else moves accordingly. So the point 1, 0 becomes 3, 0, and then the point e, -1 becomes e plus 2, -1. So I don't know where here. It's right here, e plus 2. That's 4 point something, -1. The y value doesn't change, and then we just keep on writing the same shape. that we had in the previous one. So we just took that picture, that function, and then we pull it to the right 2 units. That's all we did. Okay. All right, and then finally we're gonna take this picture and move it up 1 unit. Okay. So right here, what's happening is that we're going up 1 unit. All right. So make it more straight, this line. Okay, so since we're doing a vertical shift, going up this time, then the horizontal, the vertical asymptote stays the same, right? You take a vertical line, you move it up, it's the same line. If you had a horizontal asymptote, then that one would change. We don't have horizontal asymptote here, so we still have a vertical asymptote at x equal 2. Still a vertical asymptote, and now every point, the y value gets raised up by 1. So the point 3, 0 now becomes the point 3, 1 right here, and then the point e plus 2, -1 now actually becomes the x-intercept, right? So we have here e plus 2, the one goes up 1 unit, so now it's right here. We got the x-intercept for free, and then we graph the function. Smoother. Something like this. Okay. All right. Questions. And this is the graph. This is what we're looking for. So we can see the vertical asymptote is x equal 2, and then remember, vertical asymptote is whatever makes the argument equal to 0. In this case, is x equal 2. And we can see from the graph the domain is x bigger than 2. And you could have figured that out from the formula also, because we will need for the domain x minus 2 to be bigger than 0. And that's how you see that x has to be bigger than 2. So from 2 to infinity. Okay. Questions on how to graph logarithmic functions? At least when they come as a result of transformation. Okay, so again, any other example, it's just the same thing. The whole point is that just like what you did in college algebra, you have to be able to look at the function, break it down into all the little transformations that are happening, and you always start with your basic graph. In this case, it was ln of x, but if you're given the function, let's see, log 3 times the log base 1/2 of x minus 1, you need to understand that there are 2 transformations here. The basic function is log base 1/2 of x, so you know how to begin the picture, right? The picture begins like something like this, and with your key points, and then you're going to do 2 transformations to that picture. What is it that we're doing? Vertical stretch by a factor of 3. That's what this guy is telling you. And then we're moving the picture to the right 1 unit. If it would have been +1, then we will be moving the picture to the left 1 unit. Okay, and then you will have to modify your vertical asymptote accordingly. It will be x equals -1 in this case. But it's basically the same thing as what we had in this example. So we just do one example. So I want to do something else now. But anyways, in the homework you're gonna have several examples for graphing and so on. But it's just everything that you learned already about transformations. It's just that starting now with a new shape, which is this logarithmic shape. If the base is bigger than 1, it looks like this. If the base is less than 1, then it's a decreasing version of it. So that's all. Okay, questions on graphing logarithmic function? I'm gonna go to another ideas now. Are we okay with this? All right, so ready or not, here we go. Okay, so let's see, what did we did last time for exponentials? We studied what exponentials were. We studied the geometric properties, and by that I mean, the graph and all of that. We discussed graphing, and then we talked briefly about equations. Let's do the same thing for logarithm. Now that we know the geometric properties, let's talk a little bit about the algebraic consequences, algebraic properties, and natural thing to start is logarithmic equations. So I'm gonna do, this is part one, so examples, and we're gonna study the properties, and we're gonna look at more complicated examples. Okay, so that's the idea. So remember, guys, to mute your mic if you don't have a question. That way, it doesn't bother the class. Okay, so logarithmic equations part one. And basically, what is this? These are how to solve equations that have logarithms in them. Okay, so let's just do some simple examples. Okay, before I do that, again, what's the idea here? The idea is that we want to exploit our magic box. Like I said, you're gonna be using this box left and right. So whenever we see a logarithm, we can always translate this into an exponential form. Okay, so a to the y equals x. So that's the idea that we want to exploit here as much as we can. All right, so let's see example, solve, and let's see, let's do log base 3 of 4x minus 7 equals 2. So this is a situation in which you have an equation and then you have log of something. Something is where the x is equals the number. Okay. So whenever you have something like this, it is actually pretty straightforward to do, because all you have to do is solve for x, and to solve for x, we can use the property that we have, right? So now, what I strongly encourage you is to always write down your restrictions, because it could be that the extraneous solutions pop up when you're doing these things. Okay. So if you want to be careful, you should write down your restrictions, just like when you are doing rational equations. Okay. So what are the restrictions here for the variable? Let me write it down. So restrictions, and basically that means that whatever x is, remember, that's a fancy way of saying the domain. You have to make sure that that term 4x minus 7 is positive. So whatever you do, you have to make sure that x is bigger than 7 over 4. If after you do your algebra, it comes out that, I don't know, let's say that you get x equals -3, you immediately know that doesn't make sense, and therefore there will be no solution to the equation. Okay? Because whatever we do, our x has to be bigger than 7 over 4. Remember, you cannot do the log of something negative. All right, now that we have the restrictions in mind, then let's go ahead and solve the equation. How do we do this? Well, we use the box, right? So we have the logarithmic expression. We want to solve for x. We write it as an exponential. So 4x minus 7 is going to be equal to 3 squared. And now, you know, the rest is very simple. 4x minus 7 equals 9. So 4x is 16. And then we get x equals 4. Is this a solution to the equation? Well, we look at the restriction. 4 is bigger than 7 over 4 for sure. So we are good to go. This is our solution. And indeed, notice that if we plug in 4, what do we get? We get 16 minus 7. And that's equal to 9. And yes, log base 3 of 9 is equal to 2. That was the very first example that we did today. All right, questions? Number 1. Questions? Right? Let's do another one. How about this one? Log base x of 64 equals 2. So this time we have an equation, and it's a logarithmic equation because we see the log in here, but now the x is in the base. The first example, it was in the argument of the log, now it is in the base of the log. Okay, not a problem at all. We can just, how can we do this? Let's get rid of the log by writing this as an exponential. Okay, so we can write this. What would be the corresponding exponential form of this equation? Who can tell me? If you want to write this in the exponential form, how would it look like? So very good. So this would be x squared equals 64. Always remember. So you go counterclockwise. Base raised to whatever the log equals to, and then that's going to be equal to the argument of the log. X to the second power equals 64. So these two things are equivalent. Now remember, let's write down our restrictions because we have to be very careful here. So what are the restrictions that we have? Well, let's look at the original problem. The x now is in the base, right? So what do we know about the log? When we define logarithm, what do we say about the base? What are the restrictions on the base? We always said the base has to be positive and different than 1, right? So these are our restrictions. Whatever x we come up with, it has to be a positive number and it has to be different than 1. Otherwise, it doesn't make sense. We did not define what it means to have a log with a negative base, and we did not talk about having base 1. It makes no sense to talk about it. You understand this? All right, so now knowing this, then let's go ahead and let's answer this question. So let's see what do we get for x. Square root method, right? So we get plus or minus 8, square root of 64. So I give you two options, positive a or negative a. But because we have our restrictions, then we can just ignore the negative a, right? We know that x must be positive, and then this is the one that works. Okay, questions? Okay, good. And then finally, how about this one? Now let us use logarithm to solve an exponential equation. Again, we did that when we were doing the car, finding the value of the car, that example that we did last time. Okay, so here we want to solve for x. So we have e to the 2x equals 5. And we want to figure out what is x. Notice that this is similar to asking 2 to the x equals 3. Okay, and then you want to figure out what is x. So that's what we want to do. So let's solve this and then say, then round your answer to 3 decimal places. Okay, so let's solve this equation. So again, what's the idea? The idea is that we want to solve for x, right? So we would like to do something to this, and eventually we want to write x equals something, right? So the first thing that we need to do is we need to get rid of the exponential. Very good, Sarah. So to get rid of the exponential, what do? We write this using logs. Because if you write this as a log, then you know that the e to the 2x is going to be gone. So let's write this as a logarithm, like Sarah is pointing out. This means 2 times x equals ln of 5. So remember, log base e is ln. We already have a notation for this. Everybody okay with this first step? We just rewrote this exponential as a logarithmic statement. Everybody okay with this so far? Right, and then, well, then the rest is very simple, right? So what is x? X is going to be ln of 5 divided by 2. So this right here is the exact answer. Okay? Now, if you want to have a feeling what this is, or like in this case, we're saying round your answer to 3 decimal places, let's go ahead and let's figure out what this number is. But once again, this is the exact answer, ln of 5 over 2. Now, what is this number? Add your calculator and do ln of 5 divided by 2. So we get about 0.805. Okay. Questions? Questions on solving these easy, so to speak, cases of logarithmic equations. So notice that all we have seen is what to do when we have log equals to a number. Later we're going to see when we have more complicated expressions, logarithms are in there and so on. We'll talk about that later. Right. Are you guys okay with this? Okay, I'm asking you a very simple question. Yes or no? You okay or not? Do you need explanation in something? Okay, so remember, if someone asks you a question, you're supposed to reply, right? because I'm not looking at you, so I don't know if you're lost, if you're following what I'm saying. So this is the only feedback that I get. If you tell me in the chat or on the mic what's going on. All right, good, very good. So let's move on. Okay, so now that we have done this, then I guess the next thing is let's go to section 4.5. We have like 15 minutes left. So that's good to at least introduce the properties of logarithms. Okay, so here's what we want to do. I'm gonna write down a theorem here. I'm gonna tell you all the properties that I want to discuss with you, and then we're gonna prove those properties just to convince ourselves why these properties work. Okay? Like I said last time, remember logarithm. This is the inverse of exponential function, right? And as we saw, on the exponential side, there are a lot of exponential properties of exponents, and you know, the algebraic properties of exponentials. Let me see these exponentials. Where are they? Graph. When did I remember talking about this? Where did I write that? The property of exponents. Maybe at the beginning. Oh, here. Okay. So you see, when we have exponential, for when you have exponents, there are some algebraic properties that you have learned, your previous algebra courses. Now we saw the logarithmic function is the inverse of the exponential. So another question to ask is, okay, these algebraic properties that we have on the exponential side, so for exponents, how do they translate? Do they translate over to the logarithmic side? And if they do, how will they look like on the logarithmic side? Okay, so this is basically what I want to discuss now. There are some of these properties here that they will give you the corresponding property on the logarithmic side. For example, property number 2, the fact that when you multiply exponentials with the same base, you add the exponents, that has a consequence on the logarithmic side. We're going to see what that is, what that translates to. Same thing about property number 3 and property number 4, and so on. Okay? So this is what we're going to discuss now. What do we get on the logarithmic side? All right, so I'm just going to write the properties, and then we're going to try to justify them. I may not have time to do all of that today, so whatever we don't prove today, we're going to prove it next time. All right, so theorem. So these are properties of logarithms, and the setup here, let a be a positive number and different than 1. We're going to be using it for the base of our log. And there are several properties here. Let's see. Number 1, log base a of 1. And you will tell me some of these properties, what they are, because you already know them. Number 3, a to the power of log base a of x. Number 4, and log base a of a to the x. And then, okay, let's see. Can you tell me what's number 1? Anybody? Property number 1, log base a of 1. What is this? Very good. This is 0, right? So basically, this is saying whenever you do log of 1, you always get 0. And this doesn't require any proof. This is because a to a 0 is 1, right? I mean, that's just the definition. Okay, so how about number 2? What is this? So number 2 is equal to 1, right? And once again, this doesn't really require any proof. It follows immediately from the definition of log. That's because a to the 1 equals a. Right? There's nothing to argue here. Okay, how about number 3? Number 3 is similar to a situation that we encountered earlier today with the e and ln. Right? So what is this? Very good. So this is equal to x. And why is this? Because remember, that's because the log and exponential are inverse to each other. So if you want to justify this, we can say, well, because the function log base a of x and the function a to the x, they are inverse of each other. That's really the reason, right? They are inverse of each other. So they cancel. right? Then we cancel each other. So what's happening in number 3 is that we are applying the log function, and then we're doing the exponential. So they cancel, so you just get back original input, which is x. Very good. And then how about number 4? Same thing, right? We also get x because, again, they cancel each other. So the reason here is exactly the same. So questions about these first 4 properties. So basically, these first 4 properties, we get them for free, right? Because they follow directly from the definition of how we define log. Are we okay? We 1 through 4. Now I'm going to start writing non-trivial properties, okay? All right, so for example, 1 is the one that comes from the property of exponents that says that anything to the 0 is equal to 1. Number 2 is, I guess, a trivial exponential property, which anything to the 1 power is equal to itself, right? A to the 1 is equal to a. 3 and 4, they came from the definition of log, which is the inverse of exponential. Now, how about property number 5? Let's see. That property that we had on the exponential side that says product of exponents with the same base to add the exponents. Then that's what we, which one do you get on this side? Well, here it is. When you do the log base a of x times y, what do we get? Well, the property says that this is going to be log base a of x plus log base a of y. In other words, the logarithm of a product is the same thing as the sum of the logarithms, right? So log, what it does is it sends products to sum, okay? So, and if you think about it, and remember, log is just a fancy name for exponent. And in that property of exponentials, what did we say? We add the exponents. When you multiply exponentials, you add the exponents. So then here, that's why we're adding the log, okay? And we're gonna try to understand what this is when we do the proof. Anyways, the log of a product is the sum of the logs. It's slightly less trivial. Now, similarly, we have a property for a quotient. The log of a quotient, what is this? So once again, this follows from the property that says that when you divide exponentials with the same base, what do you do with the exponents? You subtract them, right? Well, the log of a quotient is the difference of the logs. Okay? It becomes a difference, right? So here is another property that's less trivial. It's also non-trivial, which is what do we do when we have the log of power? So let's say that we have x to the power of r. So what is this equal to? So for example, what we're doing here, this is a generalization of number 4. In number 4, you see that we're getting x, but because the base of the log is the same as the base of the exponential expression that we have in the argument. But here, x doesn't have to be the same thing as a. Basically, this property, which you're going to be using a lot, says that you can bring the power down. So this is r times log base a of x. And this actually follows from the exponential property that says exponent of an exponent, you multiply the exponents. That's what we're doing here. R is an exponent. The log also means exponent, remember? So we're multiplying the exponents. Okay? We're going to see why this works. Okay. Anyways, by the way, notice that now number 4 becomes a special case of this, because if you think about number 4, then log base a of a to the x, according to property 7, this would be x times log base a of a. And now using property number 1, log base a of a is equal to 1. So this would be x times 1, which is x. And that's how you can use property 7 and 2 to obtain property 4, for example, if you want. Right. Anyways, but of course, we need to justify property 7 first. And property 8, the one that we used last time to evaluate the value of the car, the time that it took to reach $5,000, the price of the car, it was a change of basis. So log of x base y, let's say that you don't like the base y, well, we can change the basis. And the point is that you can pick any number you like. and then you're gonna get a quotient like this. Okay. Additionally, the way that we use this property is that actually we pick a special b. You will use this, for example, if you want to evaluate a log with a calculator and you cannot put whatever base you want. For example, if you pick b equals e, this will look like ln of x or ln of y. And if also you could pick b equals 10, then this will look like log of x over log of y. And I'm picking these two special values because in your calculator, this is what you have. In most calculators, this is what you have available, the ln key and the log key. Not every calculator allows you whatever base you want. Okay, so this is called change of basis. Change of base property. Once again, it's useful, for stuff like this. Log base 2 of 3. What is this? Well, this is just ln of 3 over ln of 2. And you can put in your calculator and compute. All right, and then another property that's usually not shown in the books, but I want to show it to you because I mentioned it earlier today, is what if you have a power down here? So log base 8 to the k of x, and the point is that this is equal to, this is similar to number 7, but when you bring the power to the front, you have to flip it. So it's 1 over k times log base 8 of x. Again, to prove all this, this last property you rarely see it in the books because it follows from the ones that we have above. Okay? So this one actually you can show that it follows easily from property 7 and property 8. Actually, I'm going to leave that one to you as a homework to think about. So this one follows from 7 and 8. So try to think about how can you use property 7 and property 8 to argue property number 9. Okay, so these are the properties of logarithm, and I expect you to know these properties, okay? You are expected to know these properties. Questions? So you should be more or less familiar with these properties because you saw them back in college algebra, okay? Because I'm taking the approach like we're starting from scratch just to make sure that we have a good foundation here, okay? And again, and for number 7, I forgot to include something special, something important, and it's the fact that here the property works for any real number. Here R is any real number. It doesn't have to be an integer. Okay? Could be a fraction, could be something, a negative number, anything. R here is any real number, number 7. All right, so these are the properties of logarithms. You need to know how to use these properties. We're gonna practice this next time. But first, we need to justify these things. We did 1 through 4, no problem. I'm gonna show to you number 5. The same way that we do number 5, you can do number 6. So number 6, I will leave it to you as a homework. Then next time, we will look at 7 and 8, okay? So let's begin this and let's justify number 5. Let's see why the log of a product is the sum of the logs. To prove. And let's look at number 5. So what do we want? We want to show that log base b of x times y equals log base b of x plus log base b of y, right? This is what we want. So here is what we're gonna do. I'm gonna take this guy and I'm gonna call it name, okay? Log base b of x, I'm gonna call it m, and then log base b of y, I'm gonna call it n. And let's see how we're gonna use this. All right, so let m be equal to log base b of x, and n, I'm gonna call it log base b of y. All right, so if m is equal to log base b of x, what does that mean? What can we say about x? Writing this in exponential form, this means that x equals b to the m. And in this second case, if I call log base b of y, if I call it n, that means that y is going to be equal to b to the n. Okay? And again, why are we doing this? Well, because I want to use the properties that we know from exponents. I want to bring exponentials into the picture. All right, so with this notation now, let's see. Log base b of x times y, what is this equal to? Well, this is going to be log base b of, so x we know is b to the m, and then y we know is b to the n. Okay, now here we're going to use the property of exponents that says that when you multiply two exponentials with the same base, what do? We add the exponents, right? So we have here b to the m plus n. But when we look at this, what is this equal to? Who can tell me what is this equal to? Log base b of b to the m plus n. What happens here? This is property number 4, right? Very good. So the log cancels the exponential because now we have the same base. So here you get m plus n. So we can say by property number 4 above, and we already justified property number 4. But what was m? M is just log base b of x, right? And what was n? N is log base b of y. So there you go. We just prove that log base b of x times y equals log of x plus log of y. Everything base b. All right. Questions on this argument for number 5? All right. So notice that similarly, you can do a similar argument for number 6. You do exactly the same thing. It's just that instead of a product, right here you're gonna have a fraction, right? B over b to the m over b to the n. And then instead of a plus, then you're gonna have a minus here. Therefore, you're gonna have a minus here, and that's the subtraction that you get in the property. So number 6 is identical to number 5, the proof. So I'm gonna leave that to you, for you to write it down, so you convince yourself. Okay. So number 6 is homework. Is similar to 5. Okay, so next time we're gonna do 7 and 8. 7 is we are recording now. Okay, so the logarithmic function, it was defined as the inverse of the exponential, and therefore each of those rules of exponents that we have, they have a corresponding rule on the logarithmic side. Okay, so those were the properties that we wrote down last time. So remember that the first 4, they actually follow straight from the definition of logarithm, just because it's the inverse of the exponential function. And then the other properties that are less trivial are those 5 through 8. And then I throw in this extra property 9. I told you can do it by just looking at 7 and 8. So I'm really going to focus on 5 through 8 now. And number 5 says that the logarithm of a product equals the sum of the logarithms. In other words, if you have a product in the argument, you can split this as a sum of 2 logarithms. And what's very important here is that notice that in all of these properties, the base is always kept the same. In other words, that when you use these properties, the logs that you get, they have the same base, right? Number 6, the logarithm of a quotient is the difference of 2 logarithms. And number 7 is going to be very important for us, which is this sort of more or less power rule, you could say. It says that when you do the log of x to some power, then you can bring the exponent down, okay? So you bring the r in front of the log, and this is true for any real number. And then the change of bases, which is very useful when it comes to calculating, like doing some calculations with logs that have base other than e or 10, which many calculators do not allow you to calculate with whatever base you want, only e or 10, then you can use change of bases. All right, so last time we proved number 5, we justify why number 5 is true, and basically, you know, we took advantage of the property of exponents that says that when you multiply 2 exponentials with the same base, you add the exponents, and that actually is the property that corresponds to property number 5 on the logarithmic side. I told you number 6 is very similar, and then I asked you to do that as a homework, so let's go ahead and let's prove number 7. Okay, so number 7, so property number 7 says, what do we want here? We want to show that if you have log base a, we're using a or b. So if you have log base a of x to the r, we want to show that this is equal to r times log base a of x, okay? So this is what we want. So to do that, we're gonna apply something similar to what we did in number 5. I'm gonna take this expression here, I'm gonna call it m. So this part right here, I'm gonna call it m. So let m be equal to log base a of x. Then what does this mean? How can we write this as an exponential? Anybody? What will be the exponential form of this logarithmic statement? So if you have that m equals log base a of x, what does that mean? How do you write these using exponents?
Is it a to the m equals x?
Very good. So this means then that x equals a to the m power. Okay? All right. So with this, let's see. What is it that we want? We want log base a of x to the r. Now, using this new notation, this is the same thing as saying log base a of a to the m to the r. Now, as you know, what happens when you have an exponential, and remember, all of this is happening inside the logarithm. So what can we do with the stuff that we have in the argument? What happens when you have an exponential raised to another exponent? What do we do? We multiply the exponents, right? That's the property that we are using here. So we get here r times m. And now what is this equal to? We have log base a of a to the r times m. If you look at one of our basic properties, what does property number 4 says? Remember, the log is the inverse of the exponential, so they undo each other, they cancel each other. So number 4 says that when you have log base a of a to some power, that's just that power, right? Do you understand that? Property number 4. So whatever power you have here, that's the one that you obtain here. So that's exactly what's happening here, right? So what is this equal to? This is going to be equal to, by property number 4, r times m. So what was m to begin with? M was log base a of x. So this is r times log base a of x. And this proves rule number 7. Okay? So now you know that whenever you do log of some power, you can always bring the power down. Okay? When you apply the log to x to some exponent, you can bring the exponent down. Okay, questions? Okay, good. So that was number 7. And then finally, let us justify number 8. And number 8 is the change of basis. We have been using it a couple of times. So let's see why is it that we're allowed to do that, to pick whatever base we want. So let's see. Let's take a look at number 8. So what do we want? So in number 8, what do we want to prove? We want to show that if you have log of x base y, this is the same thing as log base b of x over log base b of y, where b is any number you want, okay? The only restriction is that it must be positive, of course, and different than 1, because that's how we define the base of a logarithm, okay? Positive and bigger than 1. Okay, so we're gonna do this, and to do this, we're gonna do the following. So we're gonna take log base y of x, and we're gonna call it a name. Okay, so we're gonna call it m. So let's take this term right here, and just like before, we call it m. Notice that all of these proofs have this a similar trick to do, right? So we're gonna let m be equal to log base y of x. So if we were to write this in the exponential form, what would this be? So that means that x equals, what does x equals to with this notation? Well, x is not equal to m. So how do you write this using exponentials? So you have the left-hand side. y to the m equal x. Very good. So x equals y to the m. Okay. All right. Good. So with this notation, then we can do the following. All right. So let's look at the top, which is log base b of x. That's the numerator. And let's rewrite it. Okay. So what is this equal to? This is going to be log base b of y to the m, right? Because that's what is x. Now, we can use property number 7, right? What does property number 7 says? Property number 7 says that we could take this guy and we can bring it to the front, right? That's what we just proved in property number 7. So let's use it. So this is going to be equal to m times log base b of y. Does everybody understand this? Right? So what do we have? If m is equal to log base b of y, so remember that from here it follows then that m is going to be equal to, let's divide both sides by log base y. So we have log base b of x over log base b of y. In other words, I just took this guy and then I divide this term with this one, okay, to solve for m. And this is exactly what we wanted, because what was m? M was log of x base y, and we just proved that that equals what we needed to show. Okay. So in other words, you can just put whatever base you want. The price that you pay is that you're gonna get a fraction as a result. Okay, questions. Number 8. Okay, perfect. So now we know that all of these properties they work. Okay, now we know that they are true. So the question is, how do we use them? All right. So now we're gonna do a bunch of examples to see how to apply these properties. So remember, you are expected to know these properties, right? I will not be asking you for the proof. This is just for your own information, so you will trust them. But you are expected to know how to use these properties. All right, so let us do examples now. So examples. So we're gonna do different type of problems. The first one is let us use this to evaluate and estimate logarithms. Okay. So first, for example, if I ask you to evaluate something like this, ln of e to the negative 4, now you can use the property to do this very easily, right? So what is this equal to? Without having to use a calculator, of course. So what would this be equal to? This is equal to negative 4. Very good. So remember, ln is log base e. Of course, now we have an alternative as well. So that would be just because ln cancels the exponential, right? What would be also an alternative? You could say, well, ln of e to the negative 4, this is equal to negative 4 times ln of e, but ln of e is 1, so negative 4 times 1, which is negative 4, okay? But of course, the first one is way faster because you just know that ln cancels the exponential. All right, here is another little example. Let us estimate a logarithm without using a calculator. So how would you do this? Without using a calculator, estimate without calculator. So without calculator, log base 6 of 97. And we want to estimate this between two consecutive integers, okay? So between two consecutive integers. Of course, we don't know exactly the value of this, but we would like to know just by looking at it quickly between what and what numbers is this, okay? So what is it? Is this 4 point something? Is this 5 point something? Is it 2 point something? What is it? So we would like to be able to tell this without having to use a calculator, okay? And of course, let's use a calculator to compare. and see if we got it right or not. Okay? Then use a calculator to evaluate. So the point is that logarithms, we can actually estimate them very easily. And when I say estimate, is you can roughly have an idea between what and what number the logarithm is equal. Okay, exactly what it is. Well, you will need a calculator, but to estimate those is actually not that hard. Okay, so let me show you how you can do this. Okay, so here is the idea. So to do that, we're gonna actually use the property of the logarithmic function, which is that they are one-to-one and they are always monotonic, meaning when the base is bigger than 1, it's always increasing, and when the base is less than 1, it's always decreasing. So we want to take advantage of that. So the idea is to notice that when you have the logarithmic function, this is always one-to-one, and it is monotonic. In other words, it is either increasing all the time or decreasing all the time. Okay, and how do you know which one is it? Well, it depends on the base, right? If the base is bigger than 1, as you know, the function looks like this, right? Going through 1. And if the base is between 0 and 1, then the function is decreasing. Once again, going through x equal 1. So then it will look like this. All right, so that's the graph of the logarithmic function depending on the base, but in both cases it's always monotonic. So increasing, remember, what does increasing mean? Visually that the graph of the function is going up, but what does that mean algebraically in terms of the formula? So it means that if x1 is less than or equal than x2, then when you apply the function, in this case, when you apply the log function, you get that log of x1 is less than or equal than log of x2. In other words, if x1 is less than x2, the corresponding y satisfies the same inequality. So being monotonic, in this case increasing, means that the log respects the inequality. If you have a certain inequality in the input, when you apply the log, you keep the same inequality. That's what it means to be increasing. It respects the inequality. On the other hand, if you had a decreasing case, like here, what does this mean? So decreasing means that the graph is going down. Algebraically means that if x1 is less than or equal than x2, then what can we say about the logs? Now this time, as you go from left to right on the x-axis, you're going to go from top to bottom on the y-axis, so your y's are getting smaller. So this time, what happens? The log flips the direction of the inequality. So log of x1 is greater than or equal than log of x2. Okay? So this is really what it means to be a decreasing function. It means that when you apply the function to the inputs, it flips the inequality. And increasing means that it respects the inequality. Okay, we're gonna take advantage of this property. All right, so do you guys understand this? That increasing means that you respect the inequality when you apply the function, and decreasing means that you have to flip the inequality. Do you understand this? All right, so let's see how we can use this. All right, let's see how we can use this for our particular problem. So in our case, we have log, the function that we're interested in is log base 6 of x, right? That's a function that we're interested in because we want to estimate log base 6 of 97. So in this case, this is an increasing function, right? So this is increasing because 6 is bigger than 1. And so it respects inequalities. No, it doesn't flip it. That's what I mean when I say respects inequality. So it respects the inequalities. Okay, so let's see what's the idea. So you have here is how we're going to estimate log base 6 of 97. So we have here the number 97. So let's try to see if we can figure out this 97 between two consecutive powers of 6. Let's see, let's try to figure out what two consecutive powers of 6 we can find. Okay, so for example, 97 is definitely bigger than 36. Yes, which happens to be equal to 6 squared, and then is less than 216, which happens to be 6 cubed. The first thing that you need to do is locate your argument, in this case 97, between two consecutive powers of the base. And you do this, by trial and error. You start trying. So 6 to the first is 6. Okay, that's too small. 6 squared is 36, right? And then when you do 6 cubed, you see that you get 216. Okay, 97 is between 6 squared and 6 cubed. Are you okay with this so far? All right, so now what are we going to do? We're going to apply log to these inequalities, okay? Now remember the question. The question is that we're trying to estimate. So Sarah, we're trying to estimate this guy right here. We're trying to estimate log base 6 of 97 without the need of a calculator, right? Okay, so first step, you locate 97 between two consecutive powers of the base. We just did that. So now we're going to apply log to the entire inequality. So we get log base 6 of 36 is going to be less than or equal than log base 6 of 97, which is less than or equal to log base 6 of 216. And again, why do we know that? Why do we know this? Because the log base 6, that function is increasing, so it respects inequality, it doesn't flip any. And now we can calculate what is log base 6 of 36. That's equal to 2. And what is log base 6 of 216? That's equal to 3. So just by, without too much effort, we can say that log base 6 of 97 is between 2 and 3. So when you calculate that number, that's going to be 2 point something, right? So if you wanted to have a feeling more or less what log base 6 of 97 is, you can do this quickly. Find two consecutive powers of the base, and therefore the log will be between those two powers. That's basically what this is, okay? So now let's verify. Let's actually use our calculator. Let's see, before we do that, questions on this estimation that we did? You guys understand this? All right, so now let us actually evaluate this. So to evaluate, we're going to use a calculator. Now, and since my calculator does not allow me to put base 6, I'm going to change bases. So I'm going to calculate this as ln of 97 divided by ln of 6. Okay, so try it on your own. Let's see what we get. And then indeed, we get 2.55319, etc. Keeps on going that way. But at least, so we knew just by looking at it and doing that small analysis that it was between 2 and 3. It was 2 point something. It turns out that it's 2.5, etc. Okay. All right. Questions on estimating logarithms this way? Okay, good. All right, so now let's see, how can we take advantage of the other properties, the ones that are less straightforward? And these are the type of examples that you're going to be seeing. So one of the problems that you will be given, and you will need this skill in calculus, is given a logarithm, in which the argument may look like a very complicated expression. You want to use properties of logarithm to expand this as much as possible, okay? So write as a bunch of little terms and getting rid of all the powers that you could get rid of. So let me show you what I mean. So that's the first type of examples that we're going to do. So evaluate, actually number 3, we already did 2 examples. So write the logarithm. So write the logarithm as a sum or difference and then express all powers as factors if possible. All powers as factors if possible. And again, this is a skill that you're gonna need in calculus. When you start learning to take derivatives and so on, there will be a process called logarithmic differentiation, and you're gonna be using these properties to be able to do that successfully. Okay. Anyways, let's take a look at the first one so you can see what we mean. So let's say that we have here log base a of x times the square root of x squared plus 1. Okay, so here a could be any base. Okay, just putting a here because it could be any number that you want, other than 0 and 1, of course. All right, so our job is to write this as a sum or difference, and then any power that pops up, we should write it as a factor if we can. Okay, so the first thing that we can do is, first of all, realize that there is a multiplication here. Okay, so we can take advantage of property number 5 that says that when you have the log of a product, it's equal the sum of the logs, right? So this is going to be equal to log base a of x plus log base a of the square root of x squared plus 1. And what we used here was property number 5. Okay, questions on this first step? Okay, so notice that the first term here, log base a of x, this is as simple as it gets. We cannot simplify that more. The question is, can we do something with the other term? Well, there's still something that we can do, right? So here we have, so we don't touch this one. Now notice that the argument of log base a of square root of x squared plus 1, we could write that square root of x squared plus 1 to the 1/2. Remember that the problem says to express all powers as factors if possible. So in this case, we can now use property number 7 to take the 1/2 and bring it down, right? So this 1/2, we can now bring it down by using property number 7. So this is going to be equal to log base a of x plus 1/2 log base a of x squared plus 1. Here we use property number 7. Questions on this so far? Right, and now notice that there is nothing we can do. There is nothing else that we can do. There is no property that says that the log of a sum is the sum or the product of the logs. We don't have that. Okay, you cannot split that second logarithm that we have here, log base a of x squared plus 1. We cannot do anything about it. Also, these two right here, we cannot touch it. We cannot bring it down, because to bring the power down, you need to have the entire argument to that power. Here is just the x, so we cannot bring the 2 down either. So this is as far as we go, right? So we stop right here for this example. Okay, questions? Wouldn't the root be x plus 1 and that's it? No. What do you mean? So this is what you're saying? No, this is forbidden, right? So if you had this, then yes. Okay, then yes, but this, no. I mean, those two things are not equal to each other, because the square is only affecting the x. What would you factor out? There is nothing to factor in there. You could factor out an x squared if you wanted to. You could factor out an x squared, but they're gonna get 1 plus 1 over x squared. So you will obtain x square root of 1 plus 1 over x squared. Probably that's not what you want. I mean, this just got more complicated than what it was originally, right? So this is not true. Okay. All right. So okay, let's see what the confusion is. So are you saying that this will be this? Is this what you're telling me? So then you will say x plus 1. Is this what you're thinking about? So no, that's not true. The square root of a sum, the square root of a plus b, is not square root of a plus square root of b. For example, let's do an example. Let's do 4, let's see, 4 plus 5. So we know that, what do we know about this? That we know that this is equal to, on one hand, what is this? We know that this is going to be square root of 9, which is 3. So we know that this is 3. So if we were to apply this property, what do we get? If this property were true, this one up here, what would this be? Square root of 4 plus square root of 5. Square root of 4 we know is 2, right? But square root of 5, well, this square root of 5, that's 2 point something. So this is definitely not equal to 3. Okay? So be careful, okay? So now, for product is true. If you have square root of a product, it is true that this is square root of a times square root of b. And same thing for fractions. If you have a over b, this is square root of a over square root of b. But for sum and difference, no, you cannot do that. You cannot split it. Okay? All right, perfect. Okay, so I'm going to erase this. But yeah, so make sure that you guys have this clear, because those are common mistakes that happen. I mean, it would be nice, but no, fortunately, it doesn't work like that. Right, so erase this. So again, nothing that we can do about that last expression. And so how were we able to get rid of the square root? Because we wrote it as the 1/2 power, remember? Square root means to the power of 1/2, and then we can use property number 7 to bring the power down. That's what we could do here. All right, good. So let's see, do a couple more. So how about ln of x squared over x minus 1 cubed? Let's see, let's try this one. Okay, so what can we do here? What do you think would be the first step? What's the first thing that we could do? Expand this expression. Well, there is nothing to factor. I mean, what would you factor here? Okay, so honey, where are you getting the rule from? There is no rule that says that ln of a quotient is a quotient of ln's. So it would be number 6, right? Which is about difference. So remember, we have a rule that says that when you have ln of a quotient, what can you do? It would be ln of the top minus ln of the bottom. You guys okay with this? This would be property number 6. Questions? So remember, when you do a logarithm of a product, it becomes a sum. If you do logarithm of a quotient, it becomes a difference. Questions on this first step? Right? And now let's see, can we do something about this power 2 that we have here? What can we do about that power 2? So if we use property number 7, what does it say? We can bring the power down. Good. And can we do something about this power 3? Notice that is affecting the entire argument. So again, using property number 7, we can bring it down to the front. Very good. So this is going to be 2 times ln of x minus 3 times ln of x minus 1. Here we use property 7. We use it twice. Okay. Questions? Right, now let's mix this. Let's mix some products with some quotients and so on. Let's see, let's do C. How about log base 2 of square root of x squared plus 1 divided by x cubed times x plus 1 to the 4th. Okay, and understand that all of this is the argument of the log. Okay, the base is 2. Right, so our job is to write this as a single logarithm. So how do we do this? Very good. So notice that here the first thing is to break up the fraction, right? To get rid of the fraction. Very good. So we can first write this as log base 2 of the top minus log base 2 of the bottom. Everybody okay with this? That will be the first step, to break up the big fraction. So now we have two logs. We're just going to analyze each of them. Okay? So let's see. The first log. What can we do with the first log? Let me keep writing it right. And I guess I will be citing the properties. When you do it, you don't have to tell me the properties, but I'm going to be telling you the properties so that you see, when you are looking at these notes later, how to refer back to what happened. So here we use property number 6. Okay, so the first one, so very good, Maria. So we first write this. So let's make some preparations. So that's square root. Let's write it to the 1/2. Okay, and we know what we're doing that, right? So then we can bring the 1/2 down. So Maria, be careful when you write those things. It's very important that you put parentheses. So remember, what you wrote, you are implying that x squared is the only thing that the log is affecting, but really affecting the whole thing. X squared plus 1. So parentheses are very important. Okay, and then we can actually start working on the other one as well. So we know that on the first one, the next step that follows would be to bring 1/2 down. So we're gonna do that in the next step. But what can we do on the next expression? What could we do with the next one? Notice that we have a big product here, right? So we can split that as a sum. Very good, Hannah. Now, the point is that we have a minus, and because we're going to be writing this as a sum, that minus is going to affect the whole thing because the minus is affecting the logarithm, right? So you need to open a pair of parentheses and write your sum inside those parentheses. So this will be log base 2 of x cubed plus log base 2 of x plus 1 to the 4th. Okay? So again, why am I putting those parentheses? Because the minus is going to affect those expressions. Okay? So here, what did I use? What I really used now was property 5. So now there are some exponents that we can take down. We can take down the 1/2, we can take down the 3, and we can take down 4, right? We're gonna have 1/2 log base 2 of x squared plus 1. I'm gonna take down the exponents and distribute the negative at the same time, if you don't mind. We're gonna have minus 3 log base 2 of x minus 4 log base 2 of x plus 1. And this is as simple as it gets, okay? We cannot do anything else here. There's no property that allows us to do anything else. So we stop here. Okay, questions? Yes, Sarah.
Wouldn't it be the 3 log base 2x plus 4 log base 2x plus 1 instead of minus because it was an addition before? Oh, I'm sorry. You distribute the negative. My bad.
Exactly. Yeah, we have that negative in front that's affecting everything inside the parentheses.
Oh, okay, got it. Thank you.
Good. All right. Anybody else? Any questions? So here we use property 7 in the last one. Okay, perfect. So again, this is a skill that you really will need it in calculus. Okay, so right now you may say, okay, what's the point in this? And what's the big deal? Why do we even want to do this? Well, you're gonna want to do this when you get to calculus because it's gonna make your calculations way easier. Like to calculate the derivative of the function that you have originally here in part C is actually a nightmare. But if you use these properties first, and instead you calculate the derivative of this last expression that we have, it's pretty straightforward and easy to do. Some formulas that you're gonna learn in calculus. Okay, so that's when this is gonna become meaningful. All right, so this is how to expand a logarithm. Okay, so how to take a log like this and then expand it as big as you can. Well, and now what we actually want to do is the opposite. The other type of example is do it the other way. In other words, if I give you something big, like this one, I want you to write it as a single log. In other words, going back. If I give you the last expression, how do you write it as the original one that we have here? Okay? So that's the next exercise that we're going to do. How to compress big expressions, logarithmic expressions like this into a single logarithm. And that is going to be useful for us now because you can apply that to solve equations. Anyways, let's see that in action. So that was number 3. Now let's take a look at number 4. So write as a single logarithm. And basically is, doing what we just did, but backwards. So write as a single logarithm. And let's see. First one, let's do log base A of 7. Again, let's start, something simple. And then we start making it more interesting. Okay, so let's see. Log base A of 7 plus 4 times log base A of 3. All right, so if we want to write this as a single logarithm, the first thing that we need to do is, so remember, you have to use the properties with cos, okay? So the first thing that we need to do is any coefficient that we have in front of the log, we need to get rid of it. So right now, there's nothing to do about the first log, but the second one, this 4 right here, we need to get rid of it. And how do we get rid of this 4? Well, we can use property number 7 backwards. So this 4, we can bring it here as a power to the 3. Does everybody understand this? So, we're using property 7 backwards. So we can rewrite this as log base A of 7 plus log base A of 3 to the 4. Okay? But then, now why do we do this? Well, because now we have a sum of logs. And what do you know about sum of logs? What can we do about the sum of logs? We can write this as a single log, and be mindful of this, it's very important. We can do that because the bases are the same. Okay? And all we have to do is we multiply the argument. So here we use property number 7, and then here we use property number 5 backwards. Questions? All right, and then we get 81 times 7, that's 567. So this is really log base A of 567. Okay, so we managed to write that expression that we were given as a single logarithm. All right, so let's do some more examples. Again, here you just have to think backwards. Okay, so let's see, 2 over 3 ln of 8 minus 2 ln of 5 squared minus 1. That one. Then let's do, let's see, log base A of x plus log base A of 9 plus log base A of x squared plus 1. Okay, let's make it more interesting. So let's put storing in 1/2 here. And then minus log base A of 5. Right, and then I want to write a couple more, but let's first do this. Okay, so let's see for B. Once again, the first thing is this right here is just to mess with you a little bit. That's just a 24. Okay, so what you should do is just immediately write a 24 there and ignore that 5 squared plus minus 1. That's just to see if you will split that or not. So immediately, without doing anything else, if you want, you can just go ahead and write that as ln of 24. That's really not necessary at all. Okay, so you can think of this as being the original problem. All right, so now what's the first thing that we want to do? Well, before we can combine these ln's, remember, we need to get rid of any coefficient. So in this case, it's 2 over 3. We could go ahead and we could bring it up here as a power to the 8. Okay, so we can write this as ln of 8 to the 2 over 3 minus ln of 24. Okay, so before we continue, let's see, can we simplify 8 to the 2 over 3 a little bit nicer? Let's see, we have 8 to the 2 over 3. We can write 8 as 2 cubed, right? So when you multiply, you will get 2 to the 3 times 2 over 3. The 3's cancel out, so you get 2 squared. So that's just 4. Does anybody understand this? No, there are many ways to do this. So you could say 8 to the 2 over 3. This is equal to cube root of a squared, which is cube root of 64. And then cube root of 64 is equal to 4. Okay, so many ways to simplify this expression. Okay, so that's just a 4. So let's go ahead and let's write it down. So this would be ln of 4 minus ln of 24. And now, what can we do? Well, we have a difference of 2 ln's. So we can combine them by dividing the argument, right? So we get ln of 4 over 24 or ln of 1 over 6. Okay, questions? Okay, so let's see. Why don't you try the next one? So try C. I'm gonna give you 2 minutes to work on it, and then we do it together. Okay, let's see. So, anybody has an answer for this? Okay, yeah, it may be strange. All right, let's see. Let's do this together. All right. So, okay. So, are you sure about the square? It should be to the 1/2, right? All right. Yeah. Other than that, it looks good. And remember, when you have to the 1/2, it will be square root. Okay. Remember that 1/2 we translate it as a square root. If you leave it as 1/2, it's it's okay. All right. So the first thing that we do if we want to start combining this is get rid of coefficients. In other words, this 1/2 that we have here, let's bring it here as a power. Okay. All right. So let's do it. So I'm not gonna touch the rest. If you want, we can start, modifying things. This first sum that we have here, we could go ahead and combine it already because that's a sum. We can do it by multiplying, right? So that's base A, and then you multiply the arguments, and then plus, let's bring the 1/2 to the top, so that would be x squared plus 1 to the 1/2 minus log base A of 5. All right, so the square root usually type it like this, SQRT. In fact, if you go on my open math, if you type SQRT and then inside parentheses you put what you want, you will understand it as square root of what you wanted to say, instead of having to use the math palette and click in the symbol. Yeah. Right, so that's the first step. We bring the 1/2 to the top, and then we combine the first two because they were already adding. Now we see that we can keep on combining because we still have another addition here, right? These are two logs that are being added. So we can combine it together. So this would be 9x times x squared plus 1 to the 1/2. I'm going to write that already as square root of x squared plus 1, if you don't mind. And then finally, we are subtracting the logs. So now we write this as a quotient. So 9x square root of x squared plus 1, all of this divided by 5. Okay, questions? And we manage this as a single logarithm. Questions on this? Okay, so again, of course, to do this problem successfully, you need to know the properties, right? You need to know them back and forth to be able to do this type of examples. Right, let me do a couple more. How about this guy? So ln of x over x minus 1 plus ln of x plus 1 over x minus ln of x squared minus 1. Let's say that we wanted to do this one. But again, we do the same thing. So what is this? This would be ln of x over x minus 1 times x plus 1 over x. Then we have minus ln of x squared minus 1. So notice that here the x's cancel out. So we get ln of x plus 1 over x minus 1 minus ln of x squared minus 1. And now because of the difference, you can write this as ln of x plus 1 over x minus 1 over x squared minus 1. And we need to simplify this. So remember that when you simplify two fractions, because you can think of this as a squared minus 1 over 1, the denominator, you multiply and you flip the second fraction. So this becomes ln of x plus 1 over x minus 1 times 1 over x squared minus 1, which I'm going to factor. Okay? Why did I factor that? Because now this x plus 1 cancel with this, and we end up with ln of 1 over x minus 1 squared. Right. Questions with this one? Okay, good. Then you may. Yeah, I mean, you will have questions like this in which you're given a big expression and then you need to write as a single logarithm, and also the other ones as well. Expanding logarithm. Like I said, that's an important skill that you need to learn here because you're going to be using it later. Okay. All right. Any questions? let's see. Let me give you another one for you to try. Let's see. Try this one. Log base 2 of x plus log base 2 of 5 minus log base 2 of 7 plus log base 2 of x minus 1 minus log base 2 of y. It's a big logarithmic expression, a big expression. Write it as a single log. I'll give you 2 minutes. So you can actually do this very fast. Even more here that there are no coefficients. Let's see, whenever you have a bunch of sum and difference of logarithms, what does that mean? That means that you can always combine it, right? Because notice that all the bases are the same. And what's the trick? How can you do this very fast? Well, everything that's being added, anything that's showing up positive, those will be multiplied on top, and everything that you're subtracting, that means that you will eventually will be dividing by those, right? So you're gonna have a log with a fraction. Up, you're gonna have everything that was positive multiplied, and in the bottom you will have everything that was negative, multiplying that in the bottom. You understand how you can write this very quickly? So we can just write this in one shot without having to do too many steps. This is log base 2. Now what's being multiplied on top? Well, it's gonna be 5 times x minus 1, because those are the logs that are positive, over what's being multiplied in the bottom, 7 and y, because those are the logs that are negative. Okay, you can write this in one shot.